You reach out your hand, touch the table, feels solid, dense, real. But here's what nobody tells you. Your hand never touched that table. Not even close. The electrons in your skin and the electrons in that wood repelled each other at distances measured in femtometers. That's 1/quadrillionth of a meter. And what you felt as solid contact was actually electromagnetic force fields screaming at each other to stay apart. Every single thing you've ever touched in your entire life, you never actually touched. Not your phone, not your lover's face, not the ground beneath your feet. What you think is matter is 99.999% empty space held together by forces that exist everywhere and nowhere at once. And the reason that emptiness doesn't collapse into itself, the reason you're not a smoking crater right now, comes down to a principle discovered in 1925 that says two electrons can't be in the same place doing the same thing. Ever. That's it. That's what's stopping the universe from imploding. Welcome to the reality of quantum fields. About 3 to 10 femtometers for heavier elements like nitrogen or iron. The electrons orbit around this nucleus in what we call the electron cloud. That cloud extends to roughly 100,000 femtometers. Do the math. The nucleus is 100,000 times smaller in radius than the whole atom. If you scaled a hydrogen nucleus up to the size of a tennis ball, the electron cloud would stretch out to 3 miles in every direction. The nucleus contains 99.95% of the atom's mass squeezed into one part in 10 to the 15th of its volume. That leaves more than 99.999% of the atom as what looks like empty space. But here's the twist. It's not empty, not at all. That's the Bohr model from 1913, and it was debunked almost a century ago. Electrons don't orbit, they exist as probability waves, 3-dimensional density distributions that fill the entire atom. The electron isn't at one specific location. It's smeared out across a region of space defined by something called a wave function, a mathematical object that tells you the probability of finding the electron at any given point if you bother to measure it. Before you measure, the electron is everywhere in that cloud at once. The cloud is the electron. And that cloud is made of fields, quantum fields, not particles floating in emptiness. Could drop to a lower energy state by emitting a photon, conserving energy in the process. Dirac described the electromagnetic field as an ensemble of harmonic oscillators, introducing creation and annihilation operators for particles. By the late 1940s, Richard Feynman, Julian Schwinger, and Sin Itiro Tomonaga independently developed QED into a full theory. Feynman called it the joule of physics. It predicts quantities like the electron's anomalous magnetic moment to absurd precision, 1 part in 10 to the 12th. That's measuring the width of North America to within the thickness of a human hair. Julian Schwinger explained this in 1948 by calculating the first quantum correction, alpha divided by 2 pi, where alpha is the fine structure constant, roughly 1/137. Schwinger's result is engraved on his tombstone. By 2023, physicists at Harvard, led by Gerald Gabriels, measured the electron magnetic moment to 0.13 parts per trillion. The measurement came in at G divided by 2 equals 1.00115965218,059. QED theory matches this to more than 10 significant figures. No other theory in physics comes close to this level of agreement with experiment. Also, comment from which city you're hearing this from. Also, this script is researched and factual, using sources from peer-reviewed journals including the Journal of Mathematical Physics, where Freeman Dyson and Andrew Leonard published their 1967 proof of matter stability, and Physical Review D, where recent electron G-factor measurements appeared in 2023 from the Gabriels group at Harvard, showing QED predictions. Verified to unprecedented accuracy. Now back to the information. An electron isn't a tiny ball. It's a localized ripple in the electron field that permeates all of space. A photon is a ripple in the electromagnetic field. These fields exist everywhere, always, even in what we call vacuum, and they interact. When two electrons repel each other, quantum field theory describes this as an exchange of virtual photons. Not real photons you could detect, but mathematical representations in perturbation theory, lines in Feynman diagrams that represent field interactions. These virtual photons are perturbations in the electromagnetic field, caused by the presence of a charged particle. The repulsive force comes from the interference of these perturbations. The electromagnetic force is 10 to the 39th times stronger than gravity. That's 10,000 billion times stronger. For objects with balanced charges, neutral atoms, the electromagnetic forces mostly cancel out over large distances, but at atomic scales, where electrons from different atoms get close, electromagnetic repulsion dominates. The outermost electrons in your skin atoms come within a few angstroms, a few tenths of a nanometer, of the outermost electrons in the table's atoms. An angstrom is 10 to the minus 10 meters. At this distance, the electron clouds start to overlap slightly. Both sets of electrons are negatively charged, like charges repel according to Coulomb's law, formulated in 1785 by Charles Augustin de Coulomb. The force is proportional to the product of the charges and inversely proportional to the square of the distance between them. As your hand pushes down, the electrons get closer. The repulsive force increases enormously. This electromagnetic repulsion is what you feel as solidity. Your hand stops moving because the electromagnetic field between the electron clouds pushes back with equal and opposite force. Newton's third law. But there's more to it than just electromagnetic repulsion. Every electron in an atom is characterized by 4 quantum numbers: principal quantum number n, angular momentum quantum number L, magnetic quantum number m sub L, and spin quantum number m sub S, which can be plus or minus 1/2. No 2 electrons in an atom can have all 4 quantum numbers identical. This principle explains the structure of the periodic table. It explains chemical bonding, and it explains why matter doesn't collapse. Paul Ehrenfest asked in 1931, "Why are atoms so big?" His answer, only the Pauli principle. Without it, all electrons in an atom would fall into the lowest energy orbital near the nucleus. Atoms would be incredibly tiny and dense. Matter as we know it wouldn't exist. But proving this rigorously took decades. In 1967, Freeman Dyson and Andrew Leonard published their proof in the Journal of Mathematical Physics. They showed that without the Pauli Exclusion Principle, ordinary matter would collapse and occupy a much smaller volume, with energy scaling as negative n to the 7/5, where n is the number of particles. The system would be thermodynamically unstable. With the Pauli principle, the ground state energy scales linearly with n. The system is stable. Dyson later called their proof extraordinarily complicated and difficult. It was Big Bang in 1975. Elliott Lieb and Walter Thirring found a simpler proof using what's now called the Lieb-Thirring inequality. They bounded the quantum energy from below in terms of the Thomas Fermi energy, which is always stable due to a theorem by Edward Teller. Dyson wrote, "Leonard and I found a proof in 1967. Our proof was so complicated and so unilluminating that it stimulated Lieb and Thirring to find the first decent proof. When 2 fermions with the same spin approach each other, their combined wave function must be antisymmetric under particle exchange. This antisymmetry creates an effective repulsion, a resistance to identical fermions occupying the same spatial region in the same quantum state. This repulsion is short range but absolute. Combined with electromagnetic repulsion, it's responsible for the everyday observation that 2 solid objects cannot occupy the same space at the same time. When you sit on a chair, you don't fall through. Not because of mass, not primarily because of electromagnetic repulsion alone, but because the Pauli Exclusion Principle prevents the electrons in your body from occupying the same states as the electrons in the chair. In quantum electrodynamics, the interaction between charged particles is described by coupling the particle's current density to the electromagnetic potential in the Lagrangian. The electromagnetic field is quantized. Photons are the quanta, the discrete packets of energy. When 2 electrons interact, they exchange virtual photons. These aren't photons in flight that you could intercept. They're mathematical tools representing field fluctuations. The Feynman diagram for electron-electron scattering shows 2 electron lines meeting at a vertex, exchanging a wavy photon line, then continuing on. This diagram represents the first-order approximation in perturbation theory. Higher-order diagrams with more loops contribute smaller corrections. Summing all diagrams gives the full interaction. Trillions of these quantum field interactions happening simultaneously at the atomic scale. Each electron in your skin interacts with electrons in the object via the electromagnetic field. Each interaction involves virtual photon exchange. The combined effect is a classical normal force, the force perpendicular to the surface that prevents interpenetration. Classical physics emerges from quantum physics when you average over enormous numbers of particles and interactions, but at the fundamental level, everything is fields. The electrostatic repulsion between 2 protons is 1 over 10 to the 36th times weaker than... it's enormously strong at nuclear distances. Gravity between 2 protons is 10 to the negative 36 times weaker than electromagnetic repulsion. Gravity is irrelevant at atomic and nuclear scales, so why doesn't the nucleus explode? The strong nuclear force. It's roughly 100 times stronger than electromagnetic repulsion at distances less than about 1 femtometer. The strong force acts on quarks, the constituents of protons and neutrons. Each proton contains 2 up quarks and 1 down quark. Each neutron contains 1 up quark and 2 down quarks. Quarks interact via the exchange of gluons, the force carriers of the strong force described by quantum chromodynamics, QCD. At low energies, the strong force confines quarks inside protons and neutrons. At slightly larger scales, a residual strong force binds protons and neutrons together in the nucleus. This residual force is short range. It drops off rapidly beyond 1 or 2 femtometers. That's why we don't observe nuclear force effects in everyday life, but inside the nucleus, it's dominant. Protons and neutrons have a measured diameter of about 0.84 to 0.88 femtometers. The nucleus of nitrogen, 7 protons and 7 neutrons, has a radius of about 3 femtometers. The nucleons are tightly packed, with little space between them. The density of nuclear matter is roughly 10 to the 17 kilograms per cubic meter. A sugar cube of nuclear matter would weigh about 100 million tons. This is the density found in neutron stars, where gravity has compressed matter to the point where protons and electrons have merged into neutrons, and the neutron degeneracy pressure, an effect of the Pauli Exclusion Principle applied to neutrons, prevents further collapse. Neutron stars are the most rigid objects known. Their bulk modulus is 20 orders of magnitude larger than diamond. But the nucleus, dense as it is, still obeys field theory. Protons and neutrons are not elementary particles. They're composite structures made of quarks bound by gluon fields. The quarks are point-like particles as far as we can measure, down to about 10 to the negative 19 meters. Below that scale, we don't know if quarks have internal structure. They might be truly fundamental. They might not. Current experiments probed 10 to the negative 19 meters. No substructure has been found. But the point is, even inside the nucleus, even inside protons and neutrons, what exists is quantum fields and their excitations. When you think of an electron, don't picture a tiny sphere. Picture a region where the electron field has a heightened intensity, a wave packet of field energy that behaves according to the equations of quantum mechanics and quantum field theory. The electron moves through space as this wave packet propagates through the field. The electron spins, but it's not literally spinning. Spin is an intrinsic quantum property, a form of angular momentum that has no classical analog. The electron has spin 1/2, which means its spin quantum number is plus or minus 1/2 in units of h-bar, the reduced Planck constant. The Casimir effect, predicted by Hendrik Casimir in 1948 and experimentally verified in 1997, demonstrates that 2 uncharged metal plates placed very close together in vacuum experience an attractive force due to quantum fluctuations in the electromagnetic field. The vacuum isn't empty. It's a seething foam of virtual particles appearing and disappearing on timescales, dictated by the Heisenberg uncertainty. Principle. Virtual particle pairs, electron-positron pairs, quark-antiquark pairs, photon pairs, constantly pop into existence and annihilate. They can't be directly observed, but their effects are measurable. The Lamb shift, an energy difference between 2 states of the hydrogen atom that should be equal according to the Dirac equation, but aren't, is caused by the interaction of the electron with vacuum fluctuations. Measured by Willis Lamb and Robert Rutherford in 1947, explained by QED, the theoretical prediction matches the experimental value to within measurement error. It appears in formulas describing atomic spectra, the electron magnetic moment, the Lamb shift, and countless other phenomena. The value of alpha can be determined from various experiments. The most precise determination comes from the electron magnetic moment measurement combined with QED theory. In 2023, the value stood at alpha to the -1 equals 137.035-99908. 4 with an uncertainty of 0.37 parts per billion. That's 10 times more precise than any other method. A team at UC Berkeley and a team at Sorbonne University in France are working on independent measurements of alpha to resolve a slight discrepancy between recent results. The electron clouds of skin atoms approach the electron clouds of wood atoms. At a separation of a few nanometers, the electromagnetic fields begin to interact. The negatively charged electrons in your skin start to feel the repulsion from the negatively charged electrons in the wood. The electromagnetic potential increases as the distance decreases. At roughly 1 nanometer, 10 angstroms, the repulsive force becomes significant. The electron wave functions begin to overlap. The Pauli Exclusion Principle kicks in. Electrons in the same spin state cannot occupy the same region of space. The wave functions adjust to maintain antisymmetry. This adjustment increases the kinetic energy of the system. The electrons are forced into higher energy states to avoid violating the exclusion principle. This energy increase manifests as a repulsive pressure, the degeneracy pressure or exchange repulsion. The electromagnetic field and the Pauli exclusion principle together enforce the boundary. What you experience as tactile sensation, pressure, texture, temperature, is your nervous system interpreting the electromagnetic and quantum mechanical forces acting on the electrons in your skin. The table is a vast array of atomic nuclei surrounded by electron clouds, all held in relatively fixed positions by electromagnetic forces and quantum mechanical bonding. The bonds between carbon atoms in wood involve shared electrons, covalent bonds where electrons occupy molecular orbitals spanning multiple atoms. These bonds arise from the minimization of energy in the system. Electrons arrange themselves to maximize bonding and minimize repulsion, constrained by the Pauli Exclusion Principle. The resulting structure has mechanical properties: stiffness, hardness, strength. But at the fundamental level, it's all field interactions. Excitations of quantum fields. The forces holding everything together are field interactions mediated by gauge bosons, electromagnetism mediated by photons, the strong force mediated by gluons, the weak force mediated by W and Z bosons. Gravity, the fourth fundamental force, is the odd one out. General relativity describes gravity as space-time curvature, not a quantum field theory. Efforts to quantize gravity have so far failed to produce a complete theory, but at the scales of atoms and everyday objects, gravity is negligible. Electromagnetism and the Pauli Exclusion Principle govern structure and stability. The prediction of the Higgs boson, confirmed in 2012 at CERN's Large Hadron Collider, was a triumph. The Higgs field gives mass to fundamental particles through its interaction with them. Without the Higgs field, electrons and quarks would be massless. Atoms wouldn't exist. The universe would be very different. Dark matter and dark energy make up 95% of the universe's mass energy content, and we don't know what they are. The Standard Model doesn't incorporate gravity. There's a persistent discrepancy between the measured and predicted values of the muon's anomalous magnetic moment, a 4.2 sigma tension reported by the muon G-2 experiment at Fermilab in 2021. This could be a hint of new physics beyond the Standard Model, or it could be an issue with theoretical calculations involving hadronic contributions. The situation remains unresolved. Standard Model. The early universe, moments after the Big Bang, should have produced equal amounts of matter and antimatter, which would have annihilated, leaving only photons. Yet here we are, made of matter. Something broke the symmetry. We don't know what. Frontiers. Theorists are developing extensions to the Standard Model. Supersymmetry, string theory, loop quantum gravity, extra dimensions. None have been confirmed. The search continues. Appearance and sensation of solidity. The mass of objects comes mostly from the energy contained in the quark-gluon interactions inside protons and neutrons via Einstein's E equals mc squared. Only about 1% of a proton's mass comes from the masses of its constituent quarks. The rest is binding energy, the energy of the strong force field holding the quarks together. That energy has mass. You are mostly energy pretending to be matter. The fundamental particles, electrons, quarks, photons, gluons, W and Z bosons, Higgs bosons, neutrinos, are excitations of quantum fields. These fields are the fundamental reality. Particles are epiphenomena. When an electron and positron collide, they annihilate. Their energy converts into photons, excitations of the electromagnetic field. The electron and positron cease to exist as localized ripples in their respective fields. The energy propagates outward as electromagnetic radiation. Conversely, a high-energy photon passing near a nucleus can create an electron-positron pair from the energy of the electromagnetic field. Energy converts between forms. Matter and energy are interconvertible, but the fields are always there, underlying everything. The electromagnetic field has U1 symmetry, a mathematical property related to charge conservation. The strong force has SU3 symmetry, leading to color charge and confinement. The weak force, combined with electromagnetism and electroweak theory, has SU2 times U1 symmetry, broken by the Higgs mechanism. These symmetries dictate the structure of the forces and the particles. Gauge theories, quantum field theories based on local symmetries, are the language of the Standard Model. The universe is a single unified field configuration evolving according to the equations of quantum field theory and general relativity. We carve it up into particles and objects and forces for convenience, for comprehension, but the fundamental reality is more unified, more interconnected. Arranged in organs, interacting with other patterns via electromagnetic and other forces, your consciousness arises from electrochemical processes in your brain, which are ultimately quantum field interactions. The sense of self, of individuality, is an emergent property of complex systems. At the fundamental level, you are fields. Everyone is fields. Everything is fields. And when you touch something, you experience the electromagnetic force mediated by virtual photons and the Pauli Exclusion Principle preventing electron overlap. No actual contact. just fields interacting. The sensation of touch is your brain interpreting signals from mechanoreceptors in your skin, which are detecting deformations caused by electromagnetic forces at the atomic level. Reality is stranger than we evolved to perceive. Our senses give us a useful interface, solid objects, textures, colors, but that interface is a simulation, a model constructed by our brains from sensory data. The underlying reality is quantum fields. Negative n to the 7/5, gravitational binding energy alone would cause catastrophic collapse. But with the Pauli principle, fermions are forced into higher momentum states as they're compressed, increasing kinetic energy. This kinetic energy opposes gravitational collapse. The system reaches equilibrium. Matter is stable. Without this principle, atoms would be 100,000 times smaller. Molecules wouldn't form. Chemistry as we know it wouldn't exist. Life wouldn't exist. This is why electrons don't collapse into the nucleus despite being attracted by electromagnetic force. The uncertainty principle provides a minimum kinetic energy, zero-point energy, that keeps electrons in extended orbitals. Combined with the Pauli Exclusion Principle, this ensures atoms have finite size and matter has bulk. Physical explanation. He showed that the stability of bulk matter arises from a kind of uncertainty principle applying to a system of many fermions, creating a minimal kinetic energy for a given electron density. The Lieb-Thirring inequality bounds the kinetic energy from below in terms of the electron density. This lower bound is sufficient to balance the negative Coulombic energy and prove stability. The mathematical proof is intricate, but the physical insight is that quantum mechanics, via the Pauli principle and the uncertainty principle, prevents matter from collapsing despite attractive forces. For stars up to about 1.4 solar masses, the Chandrasekhar limit, the collapse is halted by electron degeneracy pressure. Electrons are packed so tightly that they fill all available low-energy states. To compress further would require forcing electrons into higher energy states, which requires work against the degeneracy pressure. The result is a white dwarf, an object about the size of Earth but with the mass of the Sun, stabilized entirely by the Pauli exclusion principle applied to electrons. Density, roughly 1 million times that of water. A neutron star results, roughly 20 kilometers in diameter, mass around 1.4 to 2 solar masses, density comparable to nuclear matter. Spin periods can be milliseconds. Magnetic fields can reach 1 billion teslas. Neutron stars are the densest stable objects in the universe, stabilized by the Pauli principle acting on neutrons. If the mass exceeds about 2 to 3 solar masses, the Tolman-Oppenheimer-Volkoff limit, even neutron. Degeneracy pressure can't prevent collapse. The object becomes a black hole. Gravity wins. It took decades to prove rigorously. Dyson and Leonard in 1967. Lieb and Thirring in 1975. Subsequent refinements and extensions. The proof that matter is stable is a major achievement of 20th century mathematical physics. They don't realize that the table holding their coffee is mostly empty space, that the forces involved are electromagnetic and quantum mechanical, that the reason the table doesn't collapse into a singularity is a principle formulated in 1925. Physics education often stops at classical mechanics. Newton's laws, conservation of energy and momentum. Quantum mechanics is reserved for specialists. But quantum mechanics is the correct description of reality. Classical mechanics is an approximation valid at macroscopic scales and low velocities. But regardless of interpretation, the mathematical formalism of quantum mechanics works. It predicts experimental results to extraordinary precision. QED is the most precisely tested theory in history. The electron magnetic moment, the Lamb shift, atomic spectra, all match theory to the limits of measurement. There are only quantum fields and their interactions. The appearance of solidity is an emergent property arising from electromagnetic repulsion between electron clouds and the Pauli exclusion principle, preventing electron overlap. The sensation of solidity is a mental construct generated by your brain in response to sensory inputs caused by these field interactions. Reality, at the fundamental level, is very different from our everyday experience. Quantum mechanics reveals that difference. Atoms are better visualized as fuzzy clouds of electron density surrounding a tiny nucleus. But even this is a simplification. The electron isn't a cloud, it's a field excitation. The atom is a configuration of interacting fields obeying the Schrödinger equation or the Dirac equation. The ideas, wave-particle duality, superposition, entanglement, the uncertainty principle, the exclusion principle, these are not esoteric. They're the foundations of chemistry, materials science, electronics, quantum computing. Students should learn that matter is mostly empty space held together by forces, that electrons behave as waves, that measurement affects systems, that reality at small scales is probabilistic, not deterministic. This would better prepare them for the 21st century, where quantum technologies are becoming practical. These technologies depend on our understanding of quantum mechanics. The more people understand the fundamentals, the better society can harness these technologies and address their implications. You realize that you are not a separate entity, but a pattern of field interactions continuous with the rest of the universe. The boundary between you and the world is fuzzy, defined by electromagnetic forces and quantum mechanics, not by any inherent separation. This can be unsettling. It can also be liberating. It shifts perspective. The Lagrangian of the Standard Model, the equation describing all known particle physics, fits on a t-shirt. It's a compact expression encoding the symmetries and interactions of all fundamental fields. From that equation, you can derive Maxwell's equations, the Dirac equation, the equations of QCD, the weak interaction, the Higgs mechanism. You can calculate scattering amplitudes, decay rates, cross-sections. The equation predicts the existence of particles before they're discovered. The W and Z bosons, the top quark, the Higgs boson. It quantifies the forces that structure the universe. It's a monument of human thought, achieved through decades of experimental work and theoretical insight. Gravitational wave astronomy reveals mergers of black holes and neutron stars. Neutrino experiments probe these elusive particles. Dark matter searches wait for rare interactions. Quantum computers grow in capability. The questions are big. Progress is steady. String theory is one candidate. It proposes that fundamental entities are not point particles, but one-dimensional strings vibrating at different frequencies. Different vibration modes correspond to different particles. Gravity arises naturally in string theory as a vibration mode of a closed string. But string theory requires extra spatial dimensions, 10 or 11 total, depending on the version. The extra dimensions must be compactified, curled up at scales too small to observe. There are many ways to compactify, leading to a vast landscape of possible universes. No unique predictions, no experimental confirmation yet. Space-time is not smooth, but composed of discrete loops and nodes forming a spin network. Loop quantum gravity avoids the infinities that plague attempts to quantize gravity using standard field theory methods. But it has its own challenges, recovering general relativity in the classical limit, making testable predictions. The field is active, no consensus. Maybe the correct theory hasn't been conceived yet. Maybe it requires new mathematics not yet invented. History suggests that major advances often involve conceptual leaps and new mathematical tools. General relativity required Riemannian geometry. Quantum mechanics required Hilbert spaces and operator algebras. Quantum field theory required distribution theory and renormalization techniques. The next step might require something we haven't thought of. These are established facts, tested and confirmed over decades. The mystery isn't whether they're true. The mystery is why they're true. Why does the universe have quantum fields? Why do fermions obey the Pauli Exclusion Principle? Why do gauge symmetries give rise to forces? These are deep questions. We don't have answers. Maybe quantum fields emerge from something more fundamental. Information, bits, qubits, some mathematical structure we haven't identified. The holographic principle suggests that all information in a volume of space can be encoded on the boundary of that volume, like a hologram. This hints that three-dimensional space might be an emergent phenomenon arising from lower-dimensional physics. ADS-CFT correspondence, a duality between a theory of gravity in anti-de Sitter space and a conformal field theory on its boundary, provides a concrete example. But ADS space is not our universe. Extending the idea to realistic cosmologies is an open problem. Asking why leads to infinite regress. At some point, you have to accept certain facts as given. The laws of physics are what they are. Why these laws and not others? Maybe there's a multiverse with different regions having different laws, and we find ourselves in a region where the laws permit complex structures and conscious observers, anthropic reasoning. Or maybe there's only one universe with one set of laws, determined by some principle we don't yet understand. What you perceive as solid contact is actually force fields interacting at femtometer distances. The table is 99.999% empty space, with mass concentrated in tiny nuclei and energy distributed in fields. Solidity is an emergent macroscopic property arising from quantum mechanics. The reason matter doesn't collapse is a principle discovered 99 years ago. This is the reality. This is the universe. Someday in the future, we might look back at quantum field theory the way we now look at Newtonian mechanics, a useful approximation of a deeper truth. Or maybe quantum field theory is the final theory of non-gravitational physics, needing only a quantum theory of gravity to complete the picture. We don't know. What we do know is that our current understanding, built on a century of experimental and theoretical work, has achieved something remarkable. A predictive, mathematically rigorous description of the microscopic world that explains the macroscopic phenomena we experience every day. The fact that pressing your hand against a table involves virtual photon exchange and Pauli exclusion is not speculation. It's tested physics. You're feeling electromagnetic fields pushing back. You're experiencing the Pauli Exclusion Principle in action. You're interacting with quantum fields. The universe, at the most fundamental level, is far stranger, far more subtle than everyday experience suggests. And that strangeness, that quantum mechanical weirdness, is what gives rise to the stable, structured, beautiful world we inhabit. Without quantum mechanics, without the Pauli principle, matter would collapse. Stars wouldn't shine. Chemistry wouldn't work. Life couldn't exist. The reason you can sit and read these words is that 99 years ago, Wolfgang Pauli figured out that no two electrons can be in the same state. And 42 years later, Freeman Dyson and Andrew Leonard proved that this makes matter stable. Solid objects are force fields, and that's the only reason anything exists at all.